Hello, welcome to another video on how to solve problems in Python. So here we have slightly more complicated problems for a non-isothermal packed bed reactor. So where a reversible gas-phase catalytic reaction occurs. So you have 2A goes to C, so reversibly. So the model predicts the variation of reactant conversion, reactor temperature, pressure along the catalyst bed, and by solving the equations, the mole balance, the energy balance, the momentum balance equation, all the relevant equations for a packed bed reactor. So we have them. So we want to solve this over a catalyst weight of 20 kilograms. So you want to see how the conversion, how the temperature, how they vary, or the concentration, how they vary along the catalyst weight. This is a common description of a packed bed reactor. So usually you write those variables with respect to the catalyst weight. Now you have the mole balance, you have the reaction rates, the energy balance, the pressure drop equation, then you have the concentration, for reactant for product, you have the rate constants. So we have K um, uh, for we have K and Kc. So because it's reversible, the temperature dependent equilibrium constant Kc, and we have reaction rate written at that, and then you have the initial conditions for X, T, and P. So what we want to do, we want to solve the model to obtain the reactor performance as a function of the catalyst weight. So how do we do this in Python that I've written for that problem? You first import all the packages similar to what we've been doing before. We still need similar packages. NumPy, solve_IVP, which you need to import from scipy.integrate, and matplotlib.pyplot, so which we import as PLT. We first, define the parameters, very important. So, and then the the equations that you have, because it's a fairly long model, so we decompose them. So we write the kinetic equation as function. So you write it pass because it depends on temperature. So K depends on temperature, Kc also depends on temperature, and then we write those as function, which that takes in temperature, the equilibrium constant, then the concentration will depend on X, T, and Y. Okay. But what we want is that we want to return the concentration of A and the concentration of C. So the concentration of the reactant and the concentration of the product. So that's what we are returning when we call this function. Okay. Now the ODEs. So the ODE system, because the reaction rate, if you look at the derivatives, say depends, they have the rate, uh, reaction rate, the dependent reaction rate, and reaction rate depends on the concentrations. So first, we need to evaluate the concentration by calling this concentration function, passing the argument, this xt, y is the input to this function, and you can unpack the variables. So x is the first, temperature is the second, and y is the third. So we'll pass this as argument when we call that function. And then the reaction rate function, you call the reaction rate function, and because you already have obtained your t values from there, it's going to pass that to this function. So the same thing, Kc, you already have unpacked the t, it's going to pass it to this function, and you obtain the rate, you calculate the rate, reaction rate from there, and then you define your differential equations. So based on the problem statement, and you return the derivatives. So because you have three derivatives, you return the three derivatives as a list. Okay. Now, how do we solve it? So to solve it, the solve_IVP will take in the function, and we take in the time span, but in this case is weight span because we are solving it over weight. This is not a lumped model. This is a distributed model. So We are solving it over weight from 0 to 20 kilograms. And then we have the initial conditions, which has been defined here for the first one is going to be X, then T, then Y. So each of them, you have X at the beginning, at 0, temperature at T naught, which has been previously defined here as 450. And then we have Y as 1. So these are the initial conditions based on the problem statement that I showed you earlier. Then when you call the function, you store the solution in this variable, solve. So you pass the function, when you call solve underscore IVP, you pass the function, the range that you want to run for, and then you pass the initial condition. But here you are specifying the method, BDM, um, backward differential, backward difference, finite difference method, basically. That's the method we want to use because this is a stiff system. So we need to use a specific or a model that can handle that. So because there are different variables are changing at different scales, so that's why it's referred to as a stiff system. So then underscore output is true. So this is not is optional, and then we uh, we define how we want the W. Remember your T eval in the previous video. So the specific weight that we want to use, the specific weight point that we want to use, we define it. So even though we are running from 0 to 20 kilograms, we want 400 points between those. Okay. And then we extract the solution. We extract the solution and we from solve.solve, then bracket W, this is how you extract the solution and you unpack those variables, X, T, and Y. So after that, we can then calculate the concentration from the function. Now we already have the X, T, and Y at different values of W. And then, because what we are trying to do is that we are trying to extract these X, T, and Y at those different points that we have. Sol has already saved the solution, but what we are doing here is to evaluate the solution at different points based on W, and that's why we've passed W. And then after that, now we have X, T, Y at different points based on W, and then we can calculate concentration that correspond to those, and then calculate pressure, and then calculate reaction rate based on the equation that we have. And then plus, we find the figure function and plot those values. So here we are plotting X against the catalyst weight. Here we are plotting the temperature against the catalyst weight. And here we are plotting the pressure against the catalyst weight. And then here we are plotting the concentration against the catalyst weight. So which is concentration of product and reactant. And then we are plotting here reaction rate as a function of the catalyst weight. Okay, I hope this makes sense. So when you run it, what do we get? You run it, then we get profiles of those variables. Yeah, you can see how the conversion varies with respect to the catalyst weight, the temperature, the pressure, the pressure drop basically. This is defined as pressure drop in the model. And then you have the concentration of the reactants going down and the concentration of the products going up, and it plateaus at some point. Okay. Then you have the reaction rate, it goes up and then it peaks and then comes down. Okay. So that's it for this video. I hope you enjoy it, and I'll see you in the next video. Bye-bye.